scale is and why it's used. And you've probably heard of the pH scale, so this will be a little bit of a review. However, you've probably never heard of pOH. So we're going to be calculating pH and pOH and looking what pOH really means, given a concentration of hydronium or hydroxide. And then we're going to be doing the flip as well, calculating concentrations based on pH or pOH. So, kind of the first thing to talk about when we're talking about pH scale is why use the scale in the first place and what's the importance? In terms of importance, the pH scale is probably the most important thing that we've talked about yet this year. pH scale is widely used. It's used for water quality and testing. Water quality, for example, is we use pH to gauge what the water will taste like. If it's slightly acidic, we can say that the water tastes quite fresh, and slightly acidic might give it a little bit of like a lemony taste. If it is neutral, if it's a pH of 7, that water will just taste bland, kind of like water. And if it's basic, you won't want to drink that water. It will taste like something's wrong with it. We also use pH scale to when we're doing food preservation, so making sure that we get our pH down to a certain level to inhibit types of bacterial growth. pH is widely used when we're looking at pollution, so we'll be looking at acid rain or acid mine runoff, things like that. And wastewater treatment, pH is always taken just to make sure that things are within a normal level. So first, before we get into some major calculations, we're going to do a little bit of a warm-up here. So with these two questions, they're both strong acid, strong base scenarios. So just kind of a reminder from the last lesson, strong acids and strong bases are things that dissociate 100% in water. So the little diagram up there on the right-hand side of the page, you can see that we've got hydrochloric acid. And when that hydrochloric acid is put in water, all of the hydrogen ions split apart from the chloride ions, and we've got 100% ionization. So with this, the warm-up says find the concentration of hydronium in a 1 molar solution of hydrochloric acid at 25 degrees Celsius. 25 degrees Celsius really doesn't mean anything for us right away. We know that this dissociates 100%, so a 1 molar solution of hydrochloric acid will also have a 1 molar solution of hydronium. With the second question here, we're also asked to find the hydronium concentration in a 1 molar solution of sodium hydroxide. This one is a strong base. So strong bases also dissociate or ionize 100%. So we know that the concentration of hydroxide is going to be 1.0 moles per liter. But now we have to transfer that into hydronium. So for that, we're going to use our Kw expression. So we've got H3O plus times OH minus is going to equal Kw. And this is where the 25 degrees Celsius comes in, because you can remember back, Kw is 1 times 10 to the negative 14 at 25 degrees Celsius. So we do our calculation and we get our concentration of hydronium is 1 times 10 to the negative 14 moles per liter. So that's a little bit of a warm-up here. Now, the other thing to think about is our pH scale. And our pH scale goes from 0 to 14, although it doesn't actually cut off there. We can actually get negative pHs, and we can have pHs go above a 14. But you'll notice with this is that if we look at the powers of these two solutions, if we look at H3O plus in the first solution, hydrochloric acid, we could rewrite that as 1 times 10 to the 0 power. So that's our pH of 0 is a 1 molar solution of strong acid. With the second solution here, you can see it's times 10 to the negative 14. That's our pH of 14. So a 1 molar strong base will give us that upper end of our pH scale. And we can go higher and lower, but it's just not normally expressed as a pH at that point. So for this lesson, I'm also going to introduce you to acid land and base land. Okay, this is, I know we're kind of getting a little bit funny talk here, but I'm going to talk about it in acid land and base land because when we're doing problems involving pH and pOH and hydroxide and hydronium, looking at all of those things, it's really important to distinguish whether we're looking at an acid situation or a base situation, because the calculations will be slightly different, and what you do is going to be calculating a pH or a pOH, and we don't want to get them mixed up. So when we're looking at acid land and base land, I like to think that there's a couple of bridges that you can use to get from one land to the other. The first one you've already talked about. We already talked about the other day, looking at that Kw. So if I want to go from the concentration of hydronium, or just hydrogen ions, sometimes expressed that way, I'm going to use that Kw value. So 1 times 10 to the negative 14 Kw divided by the hydronium concentration will give me hydroxide. And the reverse is also true. If I want to find hydronium, I can take Kw divided by hydroxide. So that's our introduction to acid land and base land. And down below, you can see all of the rest of the calculations that we're going to cover today, looking at more bridging between acid land and base land, and looking at the difference and how we flip from hydronium to pH or from hydroxide to pOH. So first, before we get into more calculations, we're going to take a look at that pH scale. pH scale we've been using for the past about 110 years. And Sorensen, it was a Danish chemist, he was the one that kind of invented the pH scale or started using it more frequently. So this is a way to specify the concentration of hydronium in a solution. And pH stands for the power or potency of hydrogen. So we're only looking at hydrogen in this particular situation. So pH scale is one of those scales that we're looking at acid land for. When we have our pH scale, the pH scale kind of goes from 0 to 14. As I said, you can go into negative pHs if you have a stronger acid than a 1 molar strong acid. You can go higher than 14 if you have stronger than or more concentrated than 1 molar strong base. But mostly the pH scale is used to measure things in between. And you can see down at the lowest pH level here, you can see that we've got a 1 times 10 to the 0 power, or a 1 molar solution hydroxide. The pH scale is a logarithmic scale. So we're going to be looking at logarithm scale and what that really means. It is a logarithmic scale, so from going from a pH of 1 to a pH of 2, we're diluting that acid by a factor of 10. If I go from 2 to 3, I'm diluting by another factor of 10. So if I've gone from 1 to 3, my acid is 100 times more dilute. Other applications of a logarithmic scale could be the Richter scale, for example. So if we're looking at earthquakes, we use the same sort of logarithmic scale to describe the earthquake. An earthquake with 5 on the Richter scale is 10 times less powerful than an earthquake with that ranks 6 on the Richter scale, for example. Another place where I've seen this very frequently reported is cases of COVID-19 when we're trying to compare levels around the world. So we'll often use a logarithmic scale so that not all the numbers will be clumped around one particular region in the graph and hard to distinguish. So keeping in mind that we're using a logarithmic scale, to calculate that pH of a solution, we're going to use the following formula. We take our pH is equal to negative log, and this is a log with base 10, of the concentration of hydronium, H3O+. So you're going to want to play around with this on your calculator to make sure that you can get the correct pH value. One thing to note when we're talking about pH and the pH scale is that sig figs, with pH, we don't start counting the sig figs until after the decimal place. So the pH itself just kind of tells us the range. After the decimal place tells us how precise that measurement was. So here's our example problem. Find the pH of a solution where the concentration of hydronium is 3.5 times 10 to the negative 3 moles per liter. So we write down our formula, plug in the 3.5 times 10 to the negative 3 moles per liter solution, and when we enter that in our calculator, we get a pH of 2.46. And you'll notice that we had 2 sig figs in the original question, 2 sig figs in the final answer there. The other thing that you'll note is there are no units associated with pH. pOH is the other scale that we can use. It's not as commonly used. You wouldn't go out and test a swimming pool and say, oh, it's got a pH of 5.2, but it also can be calculated as well, and you'll see it in some scientific texts. And the pOH similarly is negative log of the concentration of hydroxide. So this is kind of a baseline calculation. It keeps everything in that base side of things. Here's our example. Find the pOH of a solution where the concentration of hydroxide is 2.86 times 10 to the negative 12. We plug that into our calculator, and we get a pOH of 11.544. So with this one, we've got 3 sig figs in the original question, 3 sig figs in the final answer, counting from after that decimal point. I really encourage you to pause the video at this point, make sure that you can get this on your calculator as well, because every calculator is a little bit different, and just making sure that you know how to use your calculator will help you have success with these problems. Okay, so this is back to acid land and base land and looking at where these calculations fit in. You can see with these, we're staying in one of our lands, and we're just transitioning between the concentration of hydronium and pH, or between the concentration of hydroxide and pOH, staying on that same side of the land. Now, looking at another bridge between our acid land and base land comes to this calculation. At 25 degrees Celsius, our pH plus our pOH is equal to 14. So there's the significance of the 14 in our pH scale. This is only at 25 degrees Celsius, however, because that 14 relates to our Kw value. So Kw is 1 times 10 to the negative 14. That 14, we actually take the pKw. So we're going to take the negative log of our Kw value, and that's where we get the 14 from. So if you are told that we're at 52 degrees and it's given you a different Kw value, you can calculate what the pH plus the pOH will add up to by taking that negative log of whatever the Kw value is. Here is another example of a problem here. It says, what is the pH of a solution where pOH is 9.83? We're going to go ahead and assume it's 25 degrees Celsius as long as we haven't been told otherwise. So we know that pH plus pOH is 14. We'll solve for pH, and we get 4.17, no units. So this is our other transfer from acid land and base land. This is a second way over the bridge. So we could now use that Kw value to always relate hydronium and hydroxide together. This just gives us an easier way of crossing over between the acids and bases situation. So what I'd like you to do right now is pause the video, see if you can do these 3 questions in the quick check, and then turn the video back on, and I'm going to just go quickly through the answers, and I'll leave you right now. Okay, if you're back, the answers to question 1 of the quick check is 3.49, 10.599, and 1.51. So the way that we got that is we took the negative log of 3.2 times 10 to the negative 4, etc., etc. For question 2, it's a little bit more a thinking problem. It says, during a titration, the pH of a solution decreased quickly by 5 units from 8 to 3. Did the concentration of hydronium increase or decrease, and by how much? So if we're decreasing the pH, we're actually making it more acidic. And solutions that are more acidic have a higher concentration of hydronium in them. So that means that the concentration of hydronium increased. The other thing that we know is we're working with a logarithmic scale. So every time we go down by a unit, it gets 10 times more concentrated. So we can do 10 times 10 times 10 times 10 times 10. When we do that, it comes out to 10 to the 5th power, or 100,000 times more acidic. So really good things to think about when you're hearing pH values being reported and things like that. Okay, third question. We've got a 100 milliliter sample of an aqueous solution labeled as 0.1 molar hydronium is diluted to 1 liter. So we're adding more water to this solution. So we're asking if the pH of the solution increased or decreased, and by how much. Now, if we're diluting this solution, it means that my solution is going to be less concentrated. That means it's going to be less acidic. So my pH is actually going to go up. And because I am diluting by a factor of 10, that means that my pH is going to go up by 1. So there's the answers. Okay, the last thing that we have to do with this particular set is work backwards, finding the concentration of hydronium from pH and the concentration of hydroxide from a pOH. To do this, we work backwards. And so the opposite of a log, or like the anti-log, is taking that base 10s to the power of negative pH. So that's the way that we're going to do that. Now, in your calculators, there is a button for that base 10. So see if you can find that. It'll be much more convenient than always typing 10 to the power of whatever in your calculator, and you should get used to using that exponential function there. Some practice problems again. So again, pause the video and see if you can go from one to the other. Make sure that your calculator is working as well. And as well, there's a little sig fig practice here. So remember, with the sig figs, we're counting all the numbers after the decimal point with pH. With concentration of hydronium or concentration of hydroxide for that matter, we do sig figs just kind of as usual. So there's the answers to that first question. Okay. And you'll notice that if we're going from a concentration of hydronium to a pH, we're taking the negative log of that number. If we're going from the pH to a concentration of hydronium, we're taking 10 to the power of negative pH. So we're kind of going back and forth that way. With the second question here, it says during a titration, the pH at the equivalence point changed quickly. Calculate the concentration of hydronium before and after. So with these ones, I'm just going to plug in the numbers. I'm taking 10 to the negative 4.35 for that before value, taking that base 10 to the negative 9.65 for the after values, and I get my final answers. You'll notice with sig figs, before we use the if we had 4.35, that's 2 sig figs because we're counting after the decimal point. So that's what I'm reporting the final answer to. Last question here. Student calculates the pH of a sample of concentrated nitric acid to be negative 1.20. So I warned you that pH can be negative. She thinks she's made a mistake because the values are negative, and that makes sense because we don't normally report those really concentrated acids as a negative pH, but it can be done. So what we're going to do is we're just going to plug it into the question. So we're going to take that base 10 to the negative 1.20, plug that in our calculator, and we get a concentration of hydronium of 16 molar solution. And that's totally something that we would have in a back chemical storage area. We probably wouldn't let students use it because it is extremely dangerous, but it does exist. So there's no error made in that particular solution. We don't usually express pH values for there because you don't need scientific notation to express it, and expressing the molarity just conveys a little bit more information than expressing the pH because it tells you exactly how concentrated it is. So in summary, this is what we've done, this entire little graphic organizer here. So we had our acid land on the left, we had our base land on our right. We looked at two ways of getting from acid land to base land. Top one with the KW, bottom one using that pH of 14 for the whole scale. A reminder that this chart can only be used when we have 25 degrees Celsius. And then there's the ways of transitioning between our concentrations of hydronium and pH and concentrations of hydroxide and pOH and back. So there's kind of a summary for everything. Last problem here. We've got a 0.1 molar aqueous solution of aspirin. So this is a weak acid, acetylsalicylic acid, and it was found to have a pH of 2.27. So if you're kind of on the ball, you might have noticed that if this was a strong acid, this would have a pH of 1 because we'd have a concentration of hydronium of 0.10 if it dissociated 100%. Well, this one's found to have a pH of 2.27. So we want to determine the concentration of hydronium, hydroxide, and the pOH for this solution. So the first one, calculating the concentration of hydronium, we're just going to take 10 to the negative 2.24. We're taking the pH there. We get 5.4 times 10 to the negative 3. For calculating the concentration of hydroxide, I'm going to use the KW formula. And there are a couple of different ways of calculating this. This is just the one that I've chosen to do because it's nicely in order. When we solve for the concentration of hydroxide, I get 1.9 times 10 to the negative 12. So I kind of had to do a step to get over that acid land base land bridge. Lastly, to get to our pOH, I'm going to use the pH that I originally had. I'm going to take 14 minus that pH, and I get my pOH of 11.73.